Welcome. Today we're diving into the fascinating journey of the periodic table, cornerstone of modern science. The periodic table didn't always look the way it does today. In fact, it's the result of centuries of discovery, debate, and refinement. From ancient times, people have been curious about the substances that make up our world. Early civilizations recognized a handful of elements, like gold, silver, and copper, but had no idea how many more were waiting to be discovered. Let's explore how our understanding of elements evolved and how the periodic table came to be. Long before the periodic table, ancient Greeks believed everything was made from four elements: earth, water, air, and fire. This idea, though incorrect, dominated scientific thinking for centuries. Other cultures, like the Chinese, had their own elemental systems. These early theories laid the groundwork for future exploration, even though they lacked the scientific basis we have today. The search for the true building blocks of matter continued, setting the stage for the discoveries that would eventually shape the periodic table. During the Middle Ages, alchemists sought to transform base metals into gold and discover the elixir of life. While their goals were mystical, alchemists made important contributions to early chemistry. They discovered new substances and developed laboratory techniques that would later help scientists identify and isolate elements. Alchemy's blend of philosophy and experimentation kept the curiosity about matter alive, paving the way for the scientific revolution. Scientific methods improved in the 17th and 18th centuries. Chemists began discovering new elements. The invention of better laboratory equipment allowed them to isolate substances like oxygen, hydrogen, and nitrogen. Each new discovery challenged existing ideas and made it clear that the ancient four-element theory was outdated. The growing list of elements needed a new way to organize and understand them. Antoine Lavoisier, often called the father of modern chemistry, played a crucial role in redefining elements. In the late 1700s, he compiled a list of substances he considered elements based on careful experiments. Lavoisier's work helped move chemistry away from mystical ideas and toward a more scientific approach. His list included 33 elements, some of which we now know are compounds, but it was a major step forward. With more elements being discovered, scientists began searching for patterns. In the early 19th century, chemists like Johann Döbereiner noticed that certain elements had similar properties and could be grouped together. Döbereiner's triads grouped elements in threes based on their chemical behavior. While this was a small step, it hinted at a deeper order among the elements. John Newlands, an English chemist, proposed the law of octaves in 1864. He noticed that when elements were arranged by increasing atomic weight, every eighth element had similar properties, much like musical notes repeat every eighth note. Although his idea was initially ridiculed, it was an important step toward recognizing periodicity among the elements. Real breakthrough came with Dmitry Mendeleev, a Russian chemist. In 1869, Mendeleev arranged the known elements by increasing atomic weight and grouped them by similar properties. His periodic table left gaps for elements yet to be discovered, boldly predicting their existence and properties. When these elements were later found, Mendeleev's table was proven remarkably accurate, cementing his place in scientific history. Mendeleev's first periodic table was a game-changer. It organized elements into rows and columns based on their properties and atomic weights. The table's structure made it easy to see relationships between elements and predict the properties of unknown ones. This innovation transformed chemistry, making it a more systematic and predictive science. One of the most impressive aspects of Mendeleev's table was his willingness to leave gaps for elements that hadn't been discovered yet. He predicted the properties of these missing elements with remarkable accuracy. When elements like gallium and germanium were eventually found, their properties matched Mendeleev's predictions almost exactly, providing strong evidence for the periodic law. Periodic law states that the properties of elements are a periodic function of their atomic weights. This means that as you move through the table, certain properties repeat at regular intervals. This concept helped chemists understand why elements in the same column or group have similar chemical behaviors. The periodic law became the guiding principle for organizing the elements. In the late 19th century, a new group of elements was discovered: the noble gases. These elements, like helium, neon, and argon, were chemically inert and didn't fit into the existing table. Their discovery led to the addition of a new column, further refining the periodic table and demonstrating its flexibility as new elements were found. In the early 20th century, Henry Moseley made a key discovery: the atomic number, not atomic weight, determines an element's properties. Moseley's work showed that arranging elements by atomic number resolved inconsistencies in Mendeleev's table. This led to the modern periodic law and the table we use today. The modern periodic table arranges elements by increasing atomic number. Elements with similar properties are grouped in columns called groups or families, while rows are called periods. This structure makes it easy to identify trends in properties such as reactivity or atomic size across the table. Periodic table is divided into three broad categories: metals, nonmetals, and metalloids. Metals are typically shiny, conductive, and malleable. Nonmetals are more varied, often brittle and poor conductors. Metalloids have properties of both and act as a bridge between metals and nonmetals. This classification helps chemists predict how elements will behave in reactions. Groups are the columns in the periodic table, and elements in the same group share similar chemical properties. Periods are the rows, and as you move across a period, the properties of elements change in a predictable way. Understanding groups and periods is key to using the periodic table effectively. Transition metals occupy the central block of the periodic table. These elements, like iron, copper, and gold, are known for their ability to form colorful compounds and act as catalysts in chemical reactions. Their unique electron configurations give them a wide range of chemical behaviors. At the bottom of the periodic table you'll find two special rows, the lanthanides and actinides. These elements are sometimes called the inner transition metals. Lanthanides are used in electronics and magnets, while actinides include radioactive elements like uranium and plutonium. Their placement helps keep the table compact and organized. One of the most important trends in the periodic table is atomic radius. As you move down a group, atoms get larger because they have more electron shells. Across a period, atoms get smaller as the nuclear charge increases, pulling electrons closer. Understanding atomic radius helps explain many chemical behaviors. Ionization energy is the energy required to remove an electron from an atom. This value increases across a period and decreases down a group. Elements with high ionization energy, like noble gases, are less likely to lose electrons, while those with low ionization energy, like alkali metals, lose electrons easily. Electronegativity measures an atom's ability to attract electrons in a bond. This trend increases across a period and decreases down a group. Fluorine is the most electronegative element, making it highly reactive. Recognizing electronegativity trends helps chemists predict how elements will interact in compounds. Not all elements on the periodic table are found in nature. Some, like technetium and the transuranium elements, are synthetic and created in laboratories. These discoveries have expanded the periodic table and challenged scientists to understand the properties of elements that exist only for fractions of a second. New elements are discovered, they're given temporary names and symbols until officially recognized by the International Union of Pure and Applied Chemistry, IUPAC. The naming process often honors scientists, places, or properties of the element. This tradition connects the periodic table's history with ongoing scientific progress. The periodic table is a fundamental tool in science education. Students around the world use it to learn about elements, chemical reactions, and the structure of matter. Its organized layout makes complex information accessible, helping learners at all levels grasp the basics of chemistry. Beyond the classroom, the periodic table guides scientific research. Chemists use it to predict reactions, design new materials, and explore unknown elements. Its predictive power has led to breakthroughs in medicine, technology, and environmental science, making it an essential tool for discovery. Industries rely on the periodic table to develop products, from electronics to pharmaceuticals. Understanding the properties of elements helps engineers and manufacturers choose the right materials for specific applications. The periodic table's influence extends far beyond the laboratory. You might be surprised to learn how often the periodic table impacts your daily life. From the aluminum in your soda can to the lithium in your phone's battery, elements play a role in countless products. The periodic table helps us understand the materials that shape our world. Modern technology owes much to the periodic table. Semiconductors, batteries, and alloys are all designed using knowledge of elemental properties. As technology advances, scientists continue to explore the periodic table for new materials that can power the future. Elements from the periodic table are vital in medicine. From iodine in thyroid treatments to platinum in cancer drugs, understanding elements allows doctors to develop effective therapies. The periodic table's role in healthcare continues to grow as new treatments are discovered. Environmental science relies on the periodic table to track pollutants, understand nutrient cycles, and develop green technologies. Elements like carbon, nitrogen, and phosphorus are central to life and the environment. The periodic table helps scientists address global challenges like climate change and pollution. Space missions depend on the periodic table for materials that can withstand extreme conditions. Elements like titanium and aluminum are used in spacecraft, while scientists search for new elements in meteorites and cosmic dust. The periodic table is truly universal, guiding exploration beyond Earth. Artists have found inspiration in the periodic table, using elements to create pigments, sculptures, and even jewelry. The unique properties of metals and minerals allow for creative expression, blending science and art in unexpected ways. Elements are essential to nutrition and food science. Sodium, potassium, calcium, and iron are just a few examples of elements our bodies need to function. The periodic table helps nutritionists and food scientists understand how these elements support health. Energy production and storage rely on elements from the periodic table. Uranium powers nuclear plants, lithium is used in batteries, and silicon is key for solar panels. The search for sustainable energy solutions continues to draw on the periodic table's wealth of elements. Innovation often begins with the periodic table. Scientists and engineers use it to design new materials, from superconductors to biodegradable plastics. Each discovery opens new possibilities, showing how the periodic table continues to drive progress. Understanding the periodic table is crucial for safety in laboratories and industry. Knowing which elements are toxic, flammable, or reactive helps prevent accidents and protect people. Safety data sheets and hazard symbols are based on the properties of elements. The periodic table is a universal language for scientists. No matter where they are in the world, chemists can use the table to share information and collaborate. Its standardized format makes communication clear and efficient. The periodic table is a powerful data tool. It organizes vast amounts of information about elements such as atomic mass, electron configuration, and reactivity. Scientists use this data to make predictions and solve complex problems. Designers have embraced the periodic table's structure, using it as inspiration for everything from infographics to furniture. Its clear organization and visual appeal make it a favorite model for presenting complex information in a simple way. The periodic table has become a cultural icon, appearing in movies, TV shows, and even fashion. Its influence extends beyond science, symbolizing knowledge, discovery, and the quest to understand our world. The periodic table is still evolving. Scientists continue to search for new elements and explore the limits of chemistry. As technology advances, the periodic table will remain a vital tool for discovery and innovation, guiding us into the future. Despite its success, the periodic table still holds mysteries. Scientists are investigating superheavy elements and the possibility of an island of stability where new, longer-lived elements might exist. These challenges keep the periodic table at the forefront of scientific research. The evolution of the periodic table is a story of teamwork. Scientists from around the world have contributed discoveries, theories, and innovations. Collaboration continues to drive progress, showing that science is truly a global effort. Every new element discovered adds a piece to the puzzle. The periodic table is a living document, growing as our knowledge expands. Each discovery inspires new questions and fuels the excitement of scientific exploration. Periodic table's evolution is a testament to human curiosity and ingenuity. From ancient ideas to modern science, it has shaped our understanding of the universe. As we look to the future, the periodic table will continue to inspire discovery, innovation, and a deeper appreciation for the building blocks of matter.